Welcome to radar system course. Today we see the MTI and a pulse Doppler radar. So we have seen that earlier a CW radar. This one is about a CW radar. So in which we supposed to transmit a continuous wave. So this one is about your transmitting signal, and we are getting the receiving signal here. That is about the echo from the object. Now that echo here, that will, because through this particular antenna we supposed to use the switch here. So through this antenna, that is to be transmitted to the mixer. Okay, so at a mixer we supposed to get a two signal, one signal from the echo and another signal that will be the reference signal from the transmitting antenna. So this one is about our FT here. So we supposed to be transmitting the signal here. This one is about FT. This one is about your FR. Okay, so that is nothing but our echo signal. So we say that this one is about your FR. Now this FR consists of what? It consists of FT plus whatever the Doppler shift projected. Okay, so what we can say that this FR is nothing but what? A FT plus or minus FT. Okay, FT plus or minus FT. This plus or minus indicates your object or your target is receding to the radar, or what you can say that approaching to the radar. Okay, so this would, what we can say in another word, that target and a radar. Okay, this is supposed to be your target radar. Now this one is about your target. Okay, so in that case the target may be come towards the radar, approaching the radar, or receding the radar. Okay, so like, so we can say that we have the Doppler shift, there will be a plus or minus occur because of that a target. And then at a mixer we supposed to get a, this FD is to be removed, so we have only a, what you can say that a signal frequency, it consists of only echo signal. Okay, that is about your echo signal there. So and this will be removed here, and we supposed to use a Doppler filter, so that will extract only the whatever the Doppler frequency signal there. Okay, and through that we can find out what will be the identify or moving target there. Okay, so this way we can find out using a continuous wave radar. But some drawbacks are there, so that's why people have considered the another radar, because there are some echoes, and that echoes can be arrived from the nearby object or environment. So that is nothing but a clutter, and due to that clutter, so we are not able to differentiate what will be the signal from the target, is echo signal. So generally, if we consider that, if we have a transmit, that signal, echo signal is larger. Okay, so in that case we supposed to recognize that particular pulse or particular signal as a false one. So we are not able to detect exactly that there will be target or not because of that a clutter. Now to identify exactly what will be the your signal, what will be your object and all. So that's why instead of using a continuous pulse to be sent, continuous signal is to be sent, we supposed to be send a single pulse. Okay, we supposed to be send a pulses, train of a pulses, or we supposed to consider that okay continuous wave oscillator, but that is to be on and off for a given particular duration. So pulse modulated signal we supposed to send. Now consider here we use a duplexer. Okay, this one. So duplexer role is about what? At transmitting, it provides the signal in given direction. Okay, allows the signal to be passed to the given direction. And this one, you can say that a duplexer here. Okay, so this way here. And when it is to be receiving, so this will be transmitting the signal in a given direction. Okay. So now that is about a transmitting mode and a receiving. So whichever the echoes from the target observed at this device or at this antenna, so that will be directed toward the receiver. Okay, but whichever the high power signal, because this one we have a continuous signal, and that continuous signal is to be amplified. So this one, that's why we supposed to say that we are using a power amplifier. This is about a PS stands for a power amplifier. So we are using a power amplifier to amplify the pulse or to increase the power of that given particular signal. So that's why we supposed to use a power amplifier. And then because of this, we can send the signal for the long distance. It's a long range communication. Okay, so for the long distance communication, or send the signal to the longer object or larger object to the longer object, so that can be possible. So that's why we are supposed to use a power amplifier, the amplified pulse. Because of the duplexer, that amplified pulse will not come to the receiver directly, because the switch is there. That switch will act as a forward direction that will be used only for the transmitting the signal and not for the receiving. If supposed to be any signal, if suppose it goes to the receiver, so receiver may damage, because that signal is a high power signal. Okay, so at a receiver, we are getting only the echo that will be observed from the radar. And this is about your a pulse radar. Okay, this is nothing but what we can say a pulse radar. So we are getting a pulses there. Okay, we are just getting the pulses, means what we consider earlier. Okay, so what we have considered earlier, we say that a signal is to be transmitted. Okay, and we are getting the FD. Okay, Doppler shift. That Doppler shift, if we consider that, a Doppler shift, it is depending upon that what will be the velocity of the moving target. Now, as we have mentioned earlier, okay, we said that earlier. So we have the a object. Okay, suppose I consider that this one is about your transmitting antenna now. Okay, so this one is about your transmitting antenna. Okay, this one we have divided. Now, okay, now it is this one is transmitting the signal, and we have the your target. Okay, this one is about your object. This one is nothing but supposed to be considered as a target now. So now what happened? We send a transmitting signal. We sending the pulses here, but the direction of the target. This one is about the direction. Okay, this target is moving in the given direction. So what will be the radial velocity of the given particular target? And from this radial velocity, we can find out what will be the range here. So generally, range is what? Time taken by the signal to travel toward the target. That is a one-way signal. And again that time taken by the signal that will be reflecting from this target. That is about the echo. So this one is about ongoing signal, transmitting signal, and then it will be received. So that is about the echo. So that is about it. That is transmitting and receiving. So that's why we are getting the range from this antenna, or we can say that from this radar to the target. R is equal to what? A C, that will be the time, that is about a transit time. Transit time for what? We are supposed to be transmitting the signal toward the radar, toward the object. Okay, we send the signal from the radar to the object, and then it will be revert back. So that's why we say that CTR. And this one, okay, this is about what we can say that time is nothing but time from transmitting as well as a receiving time. Okay, so that is about its time. So we can say that a transit time. Okay, so how much is the T here? Now with this we can find out. So what will be the a Doppler shift? So Doppler shift, because we send a signal, because this object is moving and so target is moving. So because of the target moving, there is a small shift in a frequency at a receiver. So that is called as a Doppler shift. And that Doppler shift frequency is depending upon that what will be the radial velocity. Okay, so from this we say that this target has some radial velocity, and that radial velocity is depending upon that what will be the angle theta makes with the line of sight and this at actual direction of this target here. So we can say that if VR is equal to what? V cos theta. Okay, Vr is equal to V cos theta. V is nothing but that what? A velocity of the a target. So this one is nothing but the velocity of a target, and we say that Vr is equal to V cos theta. And this one we say a range here. Now from this R we can find out, so what will be the a Doppler shift. The Doppler shift from this radial velocity we can write a Doppler shift is equal to Doppler shift is equal to twice of whatever the radial velocity we have with respect to the a lambda. Okay, now that lambda is nothing but what? We send a signal, and for this signal there will be a shift occurs. Okay, so from this we can find out the what will be the a Doppler frequency shift occurs. Or we can write in another way, we say that we have what will be the transmitting frequency signal, what will be the VR by C here. So we can write that lambda. Okay, so we are just replacing the lambda with respect to whatever the signal frequency we have. Okay, that is about a transmitting signal frequency. So we'll get the a Doppler shifting. Now in the case of here pulse frequency signal, pulse Doppler radar here, to identify a target. Okay, so we consider that. So what will be the a transit time? Okay, so now in this block diagram, if you see here, we require a amplifier, power amplifier, to transmit the signal, and then the same signal. Okay, same signal we are getting that signal in terms of a sinusoidal. We are writing that is about AT, that is about amplitude of a transmitting signal. Sine of f of t is nothing but a transmitting frequency into t. Okay, that is about a transmitting. Now that signal is given as a reference to the receiver. Here we are getting a two signal. So this receiver is act as a mixer. At this particular stage, we are getting a two signal. One is about the echo signal here, and one is from the reference signal. Okay, so after that, we supposed to remove that. What will be the FT, and then we use a Doppler filter. So we supposed to use only a pass band filter, and then we'll get the FT here. Now from this, what we can calculate, we can find out that, so what will be the output here? Okay, so what will be the output at this Doppler filter? Okay, so for that purpose, we supposed to know that, so what type of a signal we transmitting here. Now this particular action, we consider that here, it is called as what? The heterodyne one, because we are using a mixer here, and then we are proposed to provide a local oscillator signal, means there's nothing but a reference signal from the CW oscillator, and this one is about a mixer stage. So this is nothing but what action is called as a heterodyne. If supposed to be we are using one more mixer, in that case we can say that it is about a super heterodyne structure. Okay, it has only a single mixer. Okay, so that's why we can say that it's about it is a heterodyne. Now what will be the a received signal? Received signal is what? Sine AR, sine of twice pi ft t minus TRA. This one is about a received signal at this particular. So AR is nothing but what? A amplitude of the received signal. AT, just like similarly we have written here, AT is nothing but a amplitude of a transmitting signal. So similarly we have a AR is the amplitude of the a received signal. And then for the given particular signal, so we are saying that TR, that is about a time, that is about a round trip time, that is equal to the that we can say that round trip time that will be equal to the whatever the range we have. So how to calculate that? Okay, so we can consider that a round trip time TR is equal to twice of R by AC. Okay, so that is nothing but your round trip time. Now from this we can find out the what will be the unambiguous. Okay, so we'll talk about later what will be the unambiguous range and all. So right now we supposed to know that this one is about a round trip time and that round trip time is used to find out what will be the range here. Okay, so just like we can write even in another way also. So that is about a CTR by 2 here, or we can say that a TR. Okay, in another way we can write also TR. Okay, so this way we can write twice R by C. Okay, okay, so this one. So either we can write in terms of a range, or either we can write a TR, that is about it in a terms of a round trip delay. Okay, so this one is about a round trip delay. Now then what will be the signal we are receiving? Generally we say that a range R, that is depending upon the what will be the object now. Okay, okay, if supposed to be we say that a target is moving. Okay, because we need to identify that a moving target. So in that case, so range will not be only the range that define, just like what will be the CTR here divided by 2. Okay, it's not only this a reference range, because range will be always changes because the target is moving. So this is about a range, initial range, and then the range is changing because the target is moving. If the target is moving, so that's why that R is changing. So R is not always with respect to CTR by 2, because it is changes with respect to what will be the relative velocity of the target. So that's why this one is about a range, and we can write here with respect to what, a relative velocity of the a target. Okay, so this one. So in that case, that velocity, that is about what you can say for a given particular target. Okay, so we can say that we have the antenna and we have the moving target now. This one is about a radial velocity. Okay, so this one is about a radial velocity. So what will be the radial velocity? That radial velocity is depending upon that what will be the speed of this target here. That's about V. So in that case, theta here, Vr is equal to V cos theta. So this is about your radial velocity. So that's why the range is always changing because the target is moving. So R is changing. R always changes here. So that's why we can see that for the given particular target, moving target, so what will be the received signal here? So what will be the output? Okay, so in another way we can say that what will be the output here we are getting. That output is depending upon this one signal, okay, f of t minus tr. But this tr, okay, this tr will changes now because we are saying that it is with respect to the a reference signal. So in that case we can write, okay, we can write here this this one now. Okay, so this one is about we can write here for the given particular. So what will be the V received here? Okay, so we will write what will be the received signal. Received signal is equal to what? AR sine of, this one is about a sine term, and we have the term that is about a twice pi ft. Okay, this is about twice pi. Now this one is changes. So t minus tr is changes. So I'll just, okay, remove this one now. This one 1 plus twice of Vr by C into T minus 4 pi Ft R0 by. Okay, so why this R0? Because R, we say that R is changes with respect to whatever the radial velocity. That's why R is equal to R0 minus Vr by Vr into T here. Okay, so that is about your radial velocity. Okay, so R is changed. So this one is about your R0. R0 is nothing but what? at the initial position, what will be the range? So we generally say that R is equal to, okay, C TR, okay, so R is equal to C TR by 2. So this one is about a C TR by 2, that is about twice of time. So now in this case, we consider that a sine of this one, and here ft of t, okay, this one is about ft into t here. So ft into this one, and this one is with respect to what, whatever the t tr0, okay, so that is about a transit time tr here, okay, so this one we can write. Now in this case we can find out that, so what will be the received frequency signal? Received frequency signal, generally we say that that is about, we can consider that earlier we say that there will be a Doppler shift, okay. Now in that case we say that a Doppler shift is nothing but what, that will be related to the, what will be the radial velocity. So we have written earlier, that is Vr by lambda, or we can say that twice of Ft into Vr by C, that we have said, we have mentioned earlier. And this Doppler shift, generally we can say that this Vr is what we can say, it is not but what, a V of cos theta, okay. So Vr is equal to V of cos theta, and there is a change with respect to, because target is in motion, so because of the target is in motion, so that there will be the angular motion or angular frequency with respect to that given target. So we can write here with respect to the, whatever the movement of the targets, we can write here omega d, because we say that there is a change in the a frequency. So we can write in terms of a twice of fd here, okay, twice by fd, okay. So that is about a Doppler frequency shift. This one will gives us the Doppler, because change with respect to time, because target is moving, so that's why that change is occur with respect to the time. So that in that case we can say that that change we can write in terms of a angular frequency. That angular frequency is what, omega d is equal to twice by ft. So this one we are getting is about a received signal, that is about a received frequency signal we are getting across the output, and that received frequency signal is nothing but what, a twice of what, ft. This one is about what we can say that a vr, okay, that is about your radial velocity of your object, or we can write in terms of a twice of vr by a lambda, and this is nothing but what, this is nothing but what we can say that a Doppler shift. Now if the target, if it is moving from the, moving toward the radar or moving away from the radar. So in that case, there is a change in the sign of the FD. We can say that there will be plus or minus sign FD. We can consider, because we say that a signal received, that FR we are receiving, that is depending upon that what will be the transmitting signal frequency, plus or minus there will be the FD. Okay, so if there will be the minus sign away from the target, if it is a plus sign, the target is approaching to the radar, okay. So whether it is approaching to the radar or receding to the radar, okay, so according to that there will be a plus or minus sign respectively here. And then if whatever the frequency signal we have at the receiver, that received frequency signal which is less than or plus, okay, plus or minus with respect to the fd there. So we can say that at a receiver, okay, so what will be the signal we are receiving, okay. So we say that signal frequency we are receiving with respect to the, what will be the difference in the reference signal. So reference signal earlier we consider that we have a reference signal sine of twice pi ft into t. Okay, this one is about a reference signal we are providing. Okay, so what is this one? A reference signal, because we are saying that receiving signal we have frequency is about ft plus or minus fd here. Okay, so at a receiver we are providing a reference to the mixer, and that reference to the mixer is nothing but what? A reference here. That is about the amplitude of the reference signal, and that reference signal consists of what will be the transmitting frequency signal, so ft here. So that's why A reference ft. And then at a receiver we are supposed to be getting a difference frequency component, and that difference frequency component is nothing but what? A Vd is equal to, that is about AD. We supposed to write instead of a sine or a cosine. For clear understanding, we are writing here in the both the way. Okay, for the simplicity, people are using the sine term. So generally, it is to be considered with respect to the cosine term. Okay, so this one is about your FDT minus 4 pi R0 by lambda. Okay, so that's about a reaching. And this one we can say that FD, this one we have, or we are writing here in the another. Okay, this one is about a receiving. And this one AD is nothing but a amplitude of what? Whatever the different signal we are receiving. Okay, so instead of a sine here, so we are writing in terms of a cosine now. Okay, so that's about it. Your signal, just we are replacing one. Okay, and that sine plus or minus, that will be depending upon the whether the object is receding the radar or approaching the radar. Okay, so this way we are getting the that particular signal. Now then we can see that what will be the uh, we are just receiving this, we are receiving the signal frequency at the particular area. Now then another issue is about, so what will be the what echo signal we are receiving at the receiver now. Okay, now consider that if your signal frequency, okay, generally we say that we are supposed to be sending the different pulses here. Okay, these are about the pulses we are supposed to be sending. Okay, so continuous waveform. Okay, so likewise, so in another way, if I draw here, so this one is about a continuous signal we are supposed to be sending here. Now this continuous signal has some particular frequency. Okay, that frequency can be what? Whatever the transmitting frequency signal we are supposed to be consider for the given particular pulses. And if we say that instead of a continuous one, we consider that a pulse Doppler radar, so then we have the pulses to be sending, and that pulse width of that pulses what we are sending, whether it is a small width or a long width. Okay, so that is about what will be the width of that particular pulse. So based on that, so we are getting that Doppler frequency at the receiver. Okay, and that consists of some particular noise. So we are not able to differentiate what will be your exactly echo signal or what will be the a what you can say that a blind target. Okay, so means we are getting the a clutter. Okay, and due to the clutter or due to any nearby object, so we are not able to detect exactly what will be the object here. Okay, so because of that, a frequency we are supposed to be using. So that's why we supposed to consider that what will be the duration of the pulse, that pulse width of whether it is a long pulse width or a small pulse width. Okay, so according to that, we supposed to say that what will be the echo signal we are receiving here. Okay, so now we'll proceed further here regarding the same. Okay, now generally we can consider that we can consider that this one is about a signal. Okay, so now I'll just draw a continuous signal now. This one is about a continuous signal. Okay, so this one is about a continuous signal. Now we can consider that in a pulse Doppler radar, instead of a continuous wave signal, we consider that some of the pulse train is to be transmitted. So that's why we are using a modulator. Okay, if you see that there is a modulator, and that modulator is used to on the transmitter and off the transmitter. Okay, so on off transmitter. So means only the section of a pulses to be transmitted, and then it is off. Again the section of pulses to be transmitted. Then what we are transmitting in another case, we are transmitting the signal. Okay, suppose I am just going to draw here right now. So we are transmitting the signal likewise. This one is about the section of pulses we are transmitting. This one, in that case, it is on. Then we are transmitting the pulses now. Then again on. Okay, so likewise, so on, off, likewise. So at a receiver, so we are getting okay signal at a receiver, that is about the echo of the same. So echo means what? It will be a similar kind of a signal we are getting at the receiver. Okay. So now what will be the echo signal we are getting? Because we say that this one is about a transmitting pulse. Okay, that because we are using a on off modulator, and then we are getting the echo, and echo consists of plus or minus FD now. Okay, so that what you can say that echo consists of what? A plus or minus FD now. Now in that case, we supposed to find out, so what will be the exactly a shift occur with respect to the whatever the echo signal we are transmitting. Now for that purpose, so we know that what will be the a transmitting frequency signal. Okay, so now what will be the width now? Okay, that is about on width. Then off, because section of pulses, train of pulses we are transmitting, and then we supposed to immediately receiving the train of the pulses before sending this one. Okay, next on off action to be occur or after that. Okay, so that we, because receiver is a separate. Okay, in impulse Doppler radar, receiver is a separate, or it works based on their separate one. Okay, so it is not dependent on the transmitter one. So when we are receiving the echo signal, because we are sending the particular pulse to be transmitted here, so in that case, echo pulses are nothing but a train of a pulses. Okay, similar kind of pulse. Maybe a frequency will be okay larger or a smaller. Okay, so higher or a smaller, lower frequency. So in that case, we can say that there will be plus or minus FD. Okay, so like now in that case, if we are not able to recognize the same pulses there, okay, at a receiver, so what will happen? So we are not able to identify there will be the target. So if that echo signals are related to the given particular frequency band, then we can say that there will be target. But again, the same signal we are getting because of the clutter, and then that because of that particular clutter, we can say that there will be a target to them, even if there is no target, but we are getting some particular signal. So our aim is about to remove that what will be the clutter of them. So that's why we supposed to find out. So what will be the Doppler frequency shift occur from the target, and what will be the whatever the signal we are receiving from the clutter there or from the environment there, and then we need to remove that signal and only supposed to be considered that a Doppler frequency shift there. Okay, so that we can we are able to identify that our object there. Then we can consider that, or we can say that we are able to recognize what will be the Doppler frequency. Again, another way we can identify that, we are supposed to know that what will be the phase shift occurring. Okay, so whatever the echo signal we transmitting, so what will be the phase shift for the given particular train of pulse. So identify that what will be the phase shift occur with the given particular train of pulses, and then we can identify whether there will be a target or not. Okay, so now detecting exactly whichever the a target, okay, and that is depending upon that what will be the Doppler frequency shift occur. If that Doppler frequency shift is more than the one cycle or less than the one cycle, okay, of a whatever the train of pulses we have. So according to that, we are able to recognize the Doppler frequency shift. Okay, so we can say that we need to know about that whatever the echo pulse train we have, if that echo pulse train we are getting, if the target is a, we are able to recognize through that a shift, okay, then we can detect whatever the shift of the shift in the particular echo train, okay, so that is about echo pulses here, and then we can find out the what will be the Doppler shift occur, and that Doppler shift occur based on the whatever the single pulse here. Okay, so generally we can consider that what will be the pulse width required to identify that whether there will be a Doppler shift or not. Okay, so in that case, if supposed to we can consider that there will be a single pulse, we can consider that a single pulse of width tau here. Okay, this is about your single pulse. Then what will be the number of cycles we require to identify that there will be a Doppler frequency shift there. Okay, within that particular pulse. So generally what happens for this given particular pulse tau, there will be at least one cycle of the Doppler frequency within the particular pulse. Okay, so within this particular single pulse, there will be a one Doppler frequency. Okay, so what we can say that means we can say that FD into tau is greater than equal to 1. Okay, so that this way we are able to detect the target. If that FD is smaller than whatever the that Doppler frequency, the Doppler that single pulse width. Okay, so in that case, I'm supposed to write here now if FD, which is smaller than whatever the single pulse width frequency. So then in that case, we are not able to detect there will be object. Okay, so this way these are the conditions here. So to identify that whether that there will be the target present or not. So the Doppler effect we can observe if we have a short pulses, or we can say that we are able to detect the aircraft if we are supposed to consider that pulses is to be a small there. Or in another case, we can say that a pulse repetition frequency is to be a larger. Okay, so what will be the pulse repetition frequency that is to be used in a pulse radar, or we can say that a moving target indicator. Okay, we can say that MTI and a pulse Doppler radar that is to be considered. So we can consider that there are some issues with low frequency and a high frequency, and if supposed to be we are using a low frequency signal. Now for example, I am supposed to say that a VHF signal now. Okay, so in that case, so for a VHF signal, what happens? So if I am going to use a VHF signal, because in the same VHF frequency signal, there are other applications. Okay, there are the other applications right now present. If we are using the VHF frequency range to identify the target, moving target, okay, if supposed to my radar is operating at a VHF frequency range, so then we are getting a clutter because there are the other applications they are working in the given VHF frequency band. So that's why we need to identify. So what will be the frequency, operating frequency of the radar so that we are able to detect the target easy, okay, or identify the target there. So aircraft detection. So mostly in the case of a military radar, okay, so their frequency range they have mentioned that are fixed, and that is exclusively to be used for the military application. Okay, so because in the given particular frequency band, other operations are not used. Okay, other applications not to be used. So that's why we are able to detect the given particular a target there. Okay, then we can say that we supposed to be detect the a target. Okay, so in that case we are able to identify so what will be the position of the given particular target. Okay, so now we can consider there a another example of a that is about a delay line canceller that is to be used mostly to identify that a whether there will be the what you can say that a blind object or not. Okay, so that's why we supposed to use a delay line canceller. So that is used to remove the whether there will be the blind target or not. Okay, and that is useful to identify that the a target clearly. So we consider here another topic. That topic is about what we can say that a sweep to sweep and delay line canceller. Okay, so now in this case, okay, so now this one is about a delay line. Now in this case, what happened here? So we supposed to consider that whatever the echo pulses we have. Okay, so we are getting the train of the echo pulses. Now this one we consider that train of the echo pulses. Okay, so this one is about a train of echo pulses. For the single pulse, we are supposed to consider that this one is about the width now. Okay, this one is about a train of echo pulse. Now, for the given particular pulses, we are getting the video pulses after the phase detector. Okay, so in that case, FD is greater than the 1 by 2. Okay, FD is to be greater than the 1 by 2. In that case, we are supposed to consider that the pulses we are receiving, okay, in the given particular width now. Okay, so likewise, we can supposed to be consider that these are about the pulses we are getting. So now we need to find out what will be the video pulses for this Doppler frequency. Okay, so in that case, we need to use a quantization to identify that what are the given particular train of a pulse system. So I'll draw here now. Just we can say that this one is about we supposed to consider that. Okay, so this way we have signal now. Okay, so likewise, so we can consider that what will be the width of the given particular pulses. Okay, and then that pulses have what we can say that there will be the indication of what or representation of that video pulses in the case of a, a positive and a negative amplitude. Okay, so because we can say that it starts with, okay, so then in that case it will be indicating there will be the positive or a negative amplitude there. Okay, and this will define you, so what will be the a moving target identification from this indicator. Means we are getting across this moving target indicator radar video. Okay, across this we are getting the video. That video is nothing but a bipolar video, and from this bipolar video we are supposed to find out the through this positive values and the negative values we are supposed to find out whether there will be the object present or not. Okay, so this way. So with this we stop here. So we see in next lecture we'll continue in next lecture. So thank you all of you. Thank you all. So maybe our meeting will end after 1 or 2 minutes. Okay, so if our meeting ends,